Okay, in this video, we're going to be talking about topic 5, addressing and routing. So we'll talk a bit about NAT devices, talk about how routers work, um, kind of how these things, how different types of routing policies get enforced and implemented and enforced. Book matching, a couple books, a couple things we've got here. Chapter 5 in computer networking, and then chapter 9.3 in computer networks, performance and quality of services. A couple of videos you might want to take a look at. Um, Video, how network address translation works. ARP, which stands for address resolution protocol. And then just another description of NAT, kind of giving you a little more detail around kind of this, what this thing is all about and how it can be implemented. Okay, there's a whole, we look at this whole TCP/IP thing. There's a couple different types of devices. All right, so one type of device is the end host. Basically, it's what we work with. So it's phones, it's computers, it's things that are sending and receiving requests over IP. All right, and it's the, as such, they are both the sources and the destination of IP packets. Routers, on the other hand, are the boxes, computers, or actually they are computers, but the systems that make up the backbone of the internet. What they will do is they'll take the traffic from the end hosts. It will identify, locate, and send packets to the destination that is requested in the packet by the end host. That was by the end host. So it will do, and there's a whole mechanism of how a packet can be routed from place to place. So routers are really kind of, think of routers as the backbone of the internet. And routers are just, basically, there are routers everywhere. There's routers, and for example, in Valley Forge, we have a router in our network. It's basically how we're connected into the internet. And then last thing we have is this idea of what we call middle boxes. And it's kind of a different kind of term, but basically what it is, it's a mechanism by which we can plug, we can put a device onto the network and be able to monitor, evaluate traffic as it flows through. So a couple of examples. We're talking a little bit more firewalls. So firewall is a packet filter that uses a set of rules. Analyzes the packets as they come through and makes decisions upon them. What is based upon what the network security policy is. And then network address translation devices. And basically it enables the utilization of a private address, for machines. So for example, theoretically everything on the internet has to have a unique address, but with IPv4, you've only got a limitation of 32 bits, which means you've got about 4 billion devices. You have more than 4 billion devices in the world. How are we able to do this? Well, one of the mechanisms they did was create something called a private namespace, or a private address space in TCP/IP, which sits behind this NAT device. So we'll be explaining kind of how these things work, over the course of this discussion. So we talked about NAT, so network address translation. Basically, what it is, and there was a standard that was developed by IETF to define a set of private internet addresses ranges. Okay, so 10.000, 172.168.168.00 and 192.168.00 are what we call private addresses. Um, and what will happen is this NAT device is structured so that it can translate the data. It can take multiple devices between on the back end, in the private namespace, and as requester pass through it to go out to the internet, it will replace the private address with a public address. And then that packet will go out. It'll be returned, and then it'll be translated back in. So that's what the address translation feature is all about. So what it really does is it really opens up a whole universe of IP addresses, and it really is one of the key factors that has allowed us to operate with the constraints of the 32-bit addresses in IP. Be able to kind of expand that and give us a little bit more breathing room. So you see this stuff. If this is usually, you'll see a lot of NATs in houses. So basically, most home computer systems, home networks, will have some sort of broadband access with a NAT, with the NAT device serving as a combination wireless access device plus firewall plus network address translation. The idea would be that your ISP, which would be some cases Comcast, some cases Verizon or others, the ISP would allocate a single address to that the home network, and then all the devices behind it, which will be running in the private space behind the NAT address, would then be able to exchange information, be able to push information across the internet. So the idea is, kind of as we say here, installed on the enterprise border router with private addresses assigned to each enterprise host. Well, the idea of a border router is, think of that as a router that communicates with the internet. It was one of the routers that handles communication with internet addressable addresses. All right. And it will not necessarily deal with the private addresses. What will happen is the NAT device will translate it into a public internet address, which can be then processed by the border routers. NAT is part, and this is kind of a byproduct, is part of what having a network address table or network address device on your network. Basically, it gives you a firewall between the internal network and the outside networks. So it serves a multiple functions. So because the idea without a network address device out there, anybody on the internet could pass through onto your local area network and access your devices and kind of monitor stuff and do all sorts of nefarious activity. The idea is it will, this idea of a NAT device, you can't connect to anything, on the external network, cannot connect to any computer on the internal network unless the internal computer initiates the contact. So what happens is you can go out across the internet and communicate with the host and get information back. However, it will not allow any host to just simply be able to connect to anything on the private network. That wasn't ever initiated off that network. So this is just some mechanics of how NAT works. Basically what it is, it's a mapping of a pool of private addresses to a public address. So as we see, it's replaced by every packet that goes through is then translated with the address as it goes out and as it comes in. the receives, he basically checks on the receiving side, determines, looks in the mapping table, determines where traffic should go, and will forward it along. And then, it can also do things like garbage collection, kind of clean up, especially as you got, you know, a lot of traffic comes through, a lot of stuff will pile up. So the idea is to kind of go through on an ongoing basis and clean up old, obsolete um, devices or device addresses that were out there. Um, Once again, some more details around this idea of mapping internal IP addresses and ports to external. So this is, a router is basically a device that will take, traffic in through into a port, into a network port, do some evaluation on the packet, and then make a decision about where it will route that packet to. Sometimes it can find an address. If you look at the packet, it'll look, because the packet will have source and destination. It'll look at the source and the destination, make a determination if it knows where it's at. If it knows where it's at, it will move it. It'll send it to that interface to send it on its way. If it doesn't, it will actually send it to the next router, which will repeat the process down the line until eventually it will find a router that knows what the end address is, and it will send it on its way. All right. So you can go through multiple, you can go through many routers. You can go through multiple hops. Uh, there is a function inside of TCP/IP TTL, what they call TTL, time to live. So obviously, as you start going farther and farther out and more hops, there's a time limit, of which it will apply until before it just drops the packet. So you'll get a timeout you'll see it as a timeout on your host machine, and the time to live just simply runs out and the packet gets dropped. So, a couple of the features, one drawback, as we say here, is, difficult for external hosts to open TCP/IP connections for hosts beyond the NAT. There's a double-edged sword here. This could be at one level, could be seen as a bad thing. Could also be seen as a good thing. If you're a security person, you don't want people. You want it to be difficult for the people on the outside to be able to come in. Sometimes in applications, what will happen is with this network address translation is actually makes things stop. So it'll kind of bring a packet in, examine, look it up in the table, replace the address. And what will happen is sometimes some applications, that delay is enough to maybe throw some stuff off, or maybe an application is using things like packet header. There's information that may be in the packet headers that might be required. So sometimes you can have issues with NAT at an application layer. Just expectations of kind of a seamless end-to-end connection, and moving it through the NAT device could potentially introduce something into the network that might mess things up a bit. So IPv6 and NAT, there are IPv6 specific NAT devices. IPv6 NAT actually is one of these things where it can, the idea of a IPv6 NAT is one potential solution where you could actually use that to use IPv6 on the internet, and then reserve private IPv4 addresses, on your local network, and you won't see the difference. So this is, so this is kind of an interesting dynamic. We'll see how this how this plays out is, the need to ultimately bite the bullet and finally get to IPv6 as we finally move to those days. So routing, basically, routing is a core function of an IP network. Right? Routers are, you know, the backbone of the internet. It's how you get things from one place to the other. So the routers are like the mail service, U.S. Postal Service. If, you give it something, it will find its destination and send it there, and then bring the result back. So you can do, so that can be stuff in a local building. That can be stuff across, a number of buildings, a number of cities, a number of countries. All right, so the IP routing is the secret sauce that enables you to kind of the internet to be a global thing. Um, so there's a couple different patterns. We say intra-domain and inter-domain. The internet is, as you look at it, it's not a homogeneous thing. Actually, there's things where you can create different domains in the internet, and so there's things called what we call interior gateway protocols and exterior gateway protocols. So for an intra-domain, IGP is used really by all the routers to be able to communicate, inside of a domain. If you want to go to another domain, you'll have to go through what we call an exterior gateway protocol, interdomain, EGP. You distribute, and what that will do is that will distribute routing information between domains. And what will happen is, the routers, as they are gathering information, will exchange information back and forth. Ultimately, get to the point where you can find any address. Ultimately, you can put anything on the internet, and you have a pretty good chance of finding its ultimate destination if it's actually on the internet. So it's just kind of an example. So this is just some examples of kind of an internetwork. With router 1, router 2 connected together. All right. So what will happen is this is a on a network connection, wireless access point here, router connected point to point, or you could be connected on a, you can either connect on a point to point, or you could just it's just another internet connection. It'll find its way through. So some examples of some intra-domain routing protocols. Some of the earliest ones is RIP. We call a distance vector protocol, routing information protocol. It's what the original one is. I think you still see it around sometimes, but for the most part, it's a kind of the older technology here. A couple other ones, OSPF, IGRP, and EIGRP are actually protocols that are intra-domain protocols that are set up by Cisco. So Cisco has these things we call distance vectors. So it can basically, that refers to the mechanisms by which the routers use to identify what is out on the internet, and kind of where is it located and how far down the wire it is. What you want to be able to do, you want these routing protocols to do is distribute the routing information to the shortest path between two routers in the domain, and in addition to also let routers recover if you have a link or a router failure. Once again, this is the IRPs. The function of the IRPs is really to distribute the aggregated routing information. And what it'll do is it will treat each domain as a black box, so you don't really know. It'll exchange the information, but it doesn't know anything else beyond that. Basically, it knows it's there and it knows how to get data to it. So we talk about the difference, like the difference of IP. So this is within a a device. So this would be like a computer here. This would be an endpoint protocol stack. This is what your TCP/IP stack looks like. Link layer, network layer. So this is your internet protocol. This is your router layer here. This is the switch layer down below. And then, above that, we have what we call the end-to-end stuff. It's the other stuff that kind of makes up the rest of the communication stack. And the routers, though, routers have, they'll have a data link layer, and then we'll have what we call the routing layer. But basically, routers only talk to, they'll put information onto the network, but they really only talk amongst themselves. So there is no kind of end to end. Basically, the routing protocol is its main function. And so what it does is it brings packets in, determines where they should go, sends them on their way, and then also talks with other routers as a communication. And communication is kind of creating this addressing model. So there's routing policies. You can actually determine what is the appropriate path. Because actually with routers you can have multiple paths to get to an endpoint. Some could be a one hop, other ones could be you can go all the way around the planet. So what'll happen is some of the design criteria or tuning criteria is, to determine what the criteria is going to be for how it's going to determine how to get something from point A to point B. So one would be things like a shortest delay, or the shortest number of hops, or the greatest available bandwidth. All right. So that is so that's kind of what a router does. I mean, a router's out there, and it's kind of, it can see, it can basically, it has lists, tables of addresses that it can look up, that it develops itself, and then it shares with other routers, and then brings data in and then sends it out. So the routing policy, import fader, which routes are accepted, export filter, which ones are advertised, and ranking, what is the best route when there's alternate routes the same way. RIP, is the earliest one. It was an early standardized protocol. It's defined RFC 2453. Occasionally RIP routers will exchange RIP messages. Used by routers and hosts to query other routers about the contents of their routing tables. Like I said, pretty simple, pretty straightforward. OSPF, another routing protocol. In this case, this is using what we call a link state routing protocol. All right. The idea is, what it will do is it will kind of chop the networks into what it calls areas. And then what will happen is it knows all about, it will have detailed information about the areas, its own areas, and kind of where things located at on the network. And then what you can do is it will, exchange information with other routers to determine, basically developing an understanding, collectively developing a understanding of what the topology of the network looks like. So there's all sorts of, OSPF has got some whole bunch of, restrictions of how you can group networks together and how things all kind of fit together. So there's, within this, an area has two types of routers: an internal router and an area border routers. Internal router, directly connected networks, belongs to the area, and area routers are attached to several areas. So the internet itself is, when you actually look at it, it actually has, it's not necessarily a single thing. It's actually 30,000 different networks in the internet. Each of those networks is called a domain. Domain is, there's a group of routers and hosts that are in the same organization. So what will happen is these, part of this, how do you get from place to place in the internet is basically how these different networks are organized and structured and exchange information to be able to ultimately find a destination. This is just some specific details around some of the interdomain routing. And just another example around that. Private domain links. The idea of allows a host inside of a domain to exchange packets with hosts in other domains. So that's actually this uh, private interdomain link. So ways to be able to kind of establish a connection, um, between two sites without necessarily having to go through the whole hierarchy of routers across multiple routers to get pointed from between two sites. Talk around kind of once again some of the internals of this stuff, interdomain interdomain routings. So you get an idea of kind of what some of the stuff that goes into decision making. The software. So this is all software that's gathering this information and kind of evaluating and looking at it. So that like you said, the routers have double duty. I mean, they're responsible for moving packets across the internet, and it's also they're also responsible for gathering the topology information and communicating amongst themselves to be able to be able to identify stuff and move stuff in an efficient fashion. Just another example. Also, interdomain routing policies. BGP is another type of routing protocol defined under RFC 4271. Um, each one kind of has its own rules of how it will, the frequency of updates and how it will update and how it does transports and things of that nature, are unique to each kind of you know each kind of routing protocol. And sometimes these things are vendor specific, as we said. We looked before. We saw some of the ones. EIGRP, IGRP, EIGRP are Cisco proprietary, so it will not exchange information with other, routers from other vendors. So BGP, we can connect a session between two routers in two different domains directly. But this never occurs automatically. So this will happen. You have to be manually configured, because what happens is this opens up the door. If you start connecting domains together through unmanaged links, obviously you've got to you could potentially have security issues. So information about kind of what what this traffic looks like as it flows through, and also some of the key decisions it needs to make. And as you start getting an idea of some of the complexities of these things, of what it takes to be able to learn and understand, um, where things are located on the internet. And that is it for topic 5.